So, welcome back to online grade 9 science in the optics unit. Today we will be taking a look at the second half of the PhET refraction simulation, as well as getting you guys started on the breakout rooms that Zoom has to offer. So what we're going to do today is we're going to review phases 1 to 3, and then I'll send you guys off into breakout rooms to do phases 4, 5, and 6. I'll spend some time describing what it is that you'll be doing and explaining those questions to you as well. So I'm going to share my screen, you guys, just so that you can see what it is that we're going to be doing today. So reviewing phases 1 to 3. When we started out in phase 1, we were just getting kind of familiar with the simulator itself, how the rays work, how the laser works, and the protractor and the different measurement tools. So ideally, we've all been able to access the simulation by clicking on the link in the OneNote, clicking play to start, and going to either intro or more tools. I'm going to skip ahead and go to more tools. You were able to drag over the protractor, setting it up on the normal at the boundary of the two media, and make use of the speed tool. So the speed measuring tool tells you the speed of light in air is 1.0 c. We know that. And we know that c, the speed of light, is equal to 3.00 times 10 to the power of 8 meters per second. Correct? Now, the reflected ray, that's still in air, is it not? Yes, it is in air. So if it's still in the air, what do we think the speed of light of the reflected ray will be?
100.
Yeah, it's going to be 1.000 as well. Yes. Now, the index of refraction of glass is 1.5, so we know it's a denser medium. Do we think the speed of light will be faster or slower in glass?
Slower.
Slower. Let's find out. It is, in fact, only 2/3, 0.67 of the speed of light in air or vacuum. So yes, it is, in fact, quite a bit slower. And that's phase 1 of the refraction inquiry simulation worksheet. Phase 1 also asked you to, that's phase 2. Phase 1 asked you just to look at the different incident angles and how they reflect. So let's review phase 1 as well. We know of a law, if any of you can use the raise hand function in Zoom to tell me what that law is called, that tells us that the incident ray angle will be equal to the reflected ray angle. And you can see that if I start at a 10, if I start at a 20 or 30, the reflected ray will always match the incident ray. I have 2 participants with their hands raised. Who are they? Let me see. Let's go with Karar.
If I recall correctly, I think it was called the law of reflection.
The law of reflection. Yes. Sorry, Christian. I saw you had your hand up there as well. You'll get the next one, okay, buddy? So yeah, the law of reflection is the law that we know of that tells us that the incident ray angle is equal to the reflected ray angle. So that's phase 1 and 2 covered. And in phase 3, we were asked to draw some conclusions based off of the differing indices of refraction. So they asked, when light passes into a medium where it slows down, does it bend toward or away from the norm? So, first of all, if it's entering a medium that's slowing it down, is that a more or less dense medium? More, right? It's entering a more dense medium. So that means its index of refraction will be higher, right?
Yeah.
So if it stays the same, if it goes from 1.2, because it says we were supposed to start out with a incident angle of 45 degrees and a index of refraction of 1.2, making the speed of light 0.83. If it stays the same, all of those others stay the same. It doesn't bend, right? But if it goes to a more dense medium, if it goes from here to a more dense medium, like let's say 1.6, it slows down. And as such, the angle bends toward or away from the normal. Christian?
Toward,
right? So let's take a look at that in the simulation. let's verify. So I'm going to adjust my index of refraction for the primary to 1.2 as it tells you to do in the worksheet. And then I'm going to adjust this one to 1.6, and I'm going to adjust my incident angle to 45 degrees. So if I look at this 45-degree angle and I turn on the angles function by clicking the box in the bottom left corner beside where it says angles, I go from, ooh, I'm not quite 45 there. I go from roughly 45 to 32. So that's significantly bent towards the normal. It's bent by about 13 degrees. That's quite significant, right? That's what phase 3 asks you to experiment with. It also asks you to make a generalized statement. So it says, what conclusions can you make from the data gathered above? Explain your reasoning and provide specific evidence with sketches if necessary to support your reason. So ideally, we've got at least a sentence or two here and maybe even a sketch that says, well, based off of the above, we know that when light travels from a less dense to a more dense medium, it slows down. As such, it bends towards the normal. When it goes from a more dense to a less dense medium, it speeds up. And as such, it bends away from the normal. Okay? So remember, the normal ray is perpendicular to the boundary, right? So if the boundary is here at 180 degrees to 0 degrees, the normal is directly perpendicular. So you see the space between the blue and the purple here? That's a straight line from 0 to 180, right? So the normal is directly perpendicular at a 90-degree angle to the boundary. So this dotted black line here is the normal. Christian, I see you got your hand up.
Yeah. So when I was doing this, so I was getting a bit confused. For example, like when it says there at the top of that table in phase 3, it says incident angles 45 degrees. I was just a bit confused. And then when you go down to the lower table, when it says like the angle equals, I didn't know if that was talking about the angle of incidence or angle of refraction.
So let me clarify, Christian. Are you referring to the chart in phase 3?
Yeah, that one.
Okay, so this is the initial incident ray. So this is telling you what the angles are for the incident ray, and then this is telling you what the indices of refraction are for the bottom area. So the indices of refraction for the top area remains constant at 1.2, and then you adjust the indices of refraction for the bottom area, and what that does is it changes the speed of light of the bottom area in the bottom medium, and then as such, it has an impact on the angle of refraction. So
that's the angle of refraction.
If I were to look at 1.6, it says that my angle of refraction should be 32 degrees. And it's 32 degrees. Right?
Okay, I got it.
If I were to change that indices of refraction to 1.0, it says it should be roughly 58. And if I click back over to my OneNote and check at 1.0, yes, it does bend to 58 degrees.
And it just shows that as the medium gets more dense, the angle of refraction begins to go more towards the normal ray.
Yes, you are correct.
Got it.
Okay, so that was phases 1 to 3. Today, we're going to go into breakout rooms, and we're going to do 4 and 5 as a group, if you wish, or independently, if you wish. And then we're going to do phase 6 as a conclusion of 4 and 5 and the entire simulation independently. So phase 4 is pretty wordy, so I'm going to explain it to you in my own words. I'm going to read it out, and then I'll reiterate to you exactly what you need to do in my own words. So follow along closely. Imagine your team has been assigned the task of looking at an incident ray traveling through the air and striking a piece of glass, and then predicting the angle of the refracted ray in the glass. Describe precisely what evidence you would need to collect in order to answer the following research question. The research question you're asking is, what incident angles will most change the direction of a ray as it passes from air into glass? Remember, when a ray of light passes from air into glass, the ray generally changes direction. That's called refraction. right? The bending, the changing of direction, the bending of the light, right? What incident angle, what angle of the incident ray, what incident angle will most change, will cause the biggest bending of the ray as it passes from air into glass? So in the simulator, which incident angle will cause the greatest bending if we go from, it has to be specifically from air to glass? Which angle will create the biggest difference? So, what information do you, as a scientist, need to gather in order to answer this question? So this is a lab inquiry-based question. Imagine we're in the lab at St. Andrews College and we have a laser on a piece of paper. Well, rather than doing a laser on a piece of paper, we're going to do the instructions for this simulation, okay? So we have a laser in the simulation. What do I need to do? Pretend I'm a grade 8 scientist and I have no idea what I'm doing when it comes to optics because I haven't learned it yet. I'm coming in with a fresh mind and I'm eager to learn. But you guys need to tell me what exactly I need to do. So how are you going to organize that? Ideally, you would start with a procedure. Tell me what I need to do. Starting with, well, I need to open the simulation, right? Then, observations. What information do I need to observe? Well, I need to know the incident ray and the refracted ray, and then I need to know the difference between the two angles to see which one had the greatest effect. Then I need some form of discussion and analysis of our data. And then I need a conclusion. So you're conducting your own little mini lab experiment, and the question is specifically given to you in phase 4. What incident angles will most change the direction of the ray as it passes from air into glass? That's phase 4. It asks you to create a detailed step-by-step description. That's your procedure. An explanation of how this can be done. That is your procedure. Okay? Not just look and see the angles, but what exactly did you do, step by step, in order to accomplish this? You might include a table and sketches. That's your observations. The goal is to be precise and detailed enough that someone else could follow your procedure. Okay, so once you've done this, you're going to answer the question in your discussion and analysis and your conclusion. Phase 5 asks you to design an answerable research question. So you're no longer being given the specific question, you're being asked to design it yourself, if that makes sense. So similar to what we did in our summative, where you guys got to choose a question. In this case, you're going to create a question and you're going to design and propose a plan to pursue the evidence. Then you're going to collect the data. Then you're going to, using the assigned simulation, like using the simulator, the PhET simulator, you're going to collect the data. And then you're going to create a conclusion, just like you did in phase 4. The only difference between phase 4 and 5 is the question is up to you. So the only difference between phase 4 and 5 is that you get to pick the question you will be researching using the simulator. In phase 5. Apologize for the slow typing. I'm working with a dislocated finger on the one hand from my snowboarding accident, but I appreciate your patience. Christian, you still have your hand up. Is that from the previous question, or do you have another? You're on mute.
I forgot to lower it.
Oh, okay. Perfect. Oops. Didn't mean to switch pages there. So, are we clear on the expectations for phase 4 and 5? Okay, great. So, any questions so far? I'm going to try and click through and see your faces. If there's a question, please use the raise hand Zoom feature or a reaction if need be. so that I can see that as I'm scrolling through. Okay, it looks like we're ready to go. Once you're done, you're gonna do a summary, a 50-word summary. All you're gonna do is discuss the path that light takes as it strikes a boundary between two different materials. Be specific and use the information from the lab that you've conducted in this online simulation to answer it. Okay, so don't go looking for outside resources and copy and paste YouTube videos. What I want you to do is I want you to think about what you've done in this simulation from phase 1 to 6 and tell me what happens to light as it passes the boundary. Does it speed down? Does it speed up? Does it bend? Does it go straight? What are the parameters? What are the things that might stipulate how the light behaves? Okay, does this make sense to everyone? Any questions so far? Okay, guys, so if there are no more questions, I'm going to stop sharing my screen and I'm going to send you guys to breakout rooms. It looks like we have roughly, okay, we have roughly 15 minutes in the breakout room. I think that's probably going to be not quite enough time for you guys to work as a group. What you might need to do, take down your partner's information at the beginning and send them a Zoom request to have a private chat. You can host your own Zoom meeting if you need more time, okay? So I'm gonna start the breakout rooms. I'll check in and help out. And if you need to, you guys can feel free to create your own Zoom meetings after this one times out. So best of luck. I'm gonna stop recording now and I'm going to send you all off to breakout rooms.